Okay, so a very good afternoon, everyone. Welcome to this week 5 of problem solving session. And today we'll be discussing about root locus diagram. So in the last week, you have gone through root locus and how you can plot root locus and what it is all about. And today we'll be solving problems on this. So so let's revise what is root locus first. So, in route criteria, we saw that a system can be stable or unstable, or that can be stable for a range of k that can be stable, and for some other values that can be unstable, right? And basically, how we judge the stability, we judge that by seeing the closed loop poles of the transfer function. Now, root locus is another way of saying whether a system is stable or like how these closed loop poles vary with k, because we saw uh, for some values of k our system is stable, and for some values of k our system is marginally stable, and for other values it's unstable. So now in root locus what we see how by changing the system parameter, that is gain in our case, how does the system behave? Like, is it stable? Does it remain stable all the time, unstable or marginally stable or whatever? So, what is root locus? Basically, it is the locus of the roots of the characteristic equation as certain parameter, that is gain in our case, a certain parameter in the system varies. Okay, so this is the definition of root locus. So we will be seeing how, like, what is the locus that we get when we vary k from 0 to infinity in our case. There is another root locus, which is called complementary root locus, for which the gain is varied between minus infinity to 0. Right, so now the first type of questions that we have in root locus stuff is we are given we are given a transfer function, and we are given a pole, and we're asked whether this pole or zero, it lies on the root locus or not. So this is the first type of questions that we have in this uh, root locus stuff, right? So to solve such a question, or in those questions we are then asked, okay, if this point lies on the root locus, then find the gain k. So for that, we need to learn the angle condition and the magnitude condition, right? But before that, I'll explain in a complex plane how we measure angles, like in different quadrants, how we measure angles. So because that will be very helpful throughout this lecture, right? So okay, so if this is a complex plane, because when we are dealing with this root locus, we are in S plane, and that is sigma and j omega. So that is a complex plane. So it is sigma and j omega, or we can write real axis or imaginary axis, right? So this is quadrant number 1. This is quadrant number 2. This is quadrant number 3. And this is quadrant number 4, right? So any complex number that is defined by its magnitude as well as angle. So if we have to find an angle, for example, if the point lies in quadrant 1, and if we have to find the angle, uh, what will be the value of angle in this quadrant 1, right? Let this angle be theta. We always take these angles in counterclockwise direction. So if we take it counterclockwise direction, the angles we take are positive. And if they are taken in negative direction, clockwise direction, then the value is negative. But I'll tell you, in some quadrants we take it clockwise, and in some quadrants we take it counterclockwise, right? So this is angle theta. So we can see in first quadrant, real part is greater than zero, as well as imaginary part is also greater than zero. In this case, this theta 1 is given by tan inverse of mod of um, y over x. Or in our case, let's assume uh, this is, in general, this is x and this is jy. So in our case, it will be, in our case, okay, let's be very specific to our notations. So in our case, it will be tan inverse of omega by sigma. Okay, so yeah. So this is the angle, how we measure the angle in the first quadrant. Now, what if we have the angle in second quadrant? Right, so again, the angle will be something like this. It will be theta 2, right? So what will be theta 2? See, this is a 0 degree. I can write it here, 0, 90, 180, then 270. Right? If I'm doing it counterclockwise, then this will be minus 90, minus 180, and 270. Right? Minus 270. If I'm going it, sorry, if I'm going it clockwise. Right? So this is, if we have angle, if we have a complex number that lies in the second quadrant, we can write it 180 minus theta, right? If it is theta, right? We can write it 180 minus theta. Or in second quadrant, how we measure the angle is write different color here. So my theta 2 will be equal to 180 minus tan inverse of omega over sigma. Correct. So, but be very careful, because sometimes when you have a complex number in second quadrant, it will be something like this. For example, minus 1 plus j omega. Then you don't need to put this minus sign in the formula, because this 180 minus tan of something, it has already taken care of this formula. So I'm giving you a full formula. You need not apply, you need not bother about the signs. Right? So when we will solve problems, whenever you have angle in the second quadrant, or whenever I'm asking you to find the angle in the second quadrant, directly apply this formula, 180 minus tan inverse of omega by sigma. Right? Similarly, if we have angle in the third quadrant, theta 3, okay, so in quadrant number 1 and quadrant number 2, we normally calculate these angles counterclockwise. But in quadrant number 3 and quadrant number 4, we calculate these angles as clockwise. That's why, for example, if I have theta 4 here, so I take it clockwise, theta 4. It will be theta 4, then it will be minus tan inverse of omega by sigma. Similarly, theta 3, I'll also take clockwise. So if it is clockwise, then it will be something like this, right? Then in my formula, it will be minus of 180 plus tan inverse omega by sigma. Right, so just remember, when we will solve problems, then it will be more clear. And it will be more clear. As of now, just remember, whenever you have a complex number in first quadrant, you will apply this formula. And whenever you have a complex number in second quadrant, you will apply this formula without bothering about the sign. And whenever you have a complex number in third quadrant, you will apply this formula, minus 180 plus tan inverse omega by sigma. And fourth quadrant, you have this. But be very careful that you should remember. So these sign convention stuff, or this way, we take the angles in first two quadrants as counterclockwise, and in the last two quadrants, that is in the third and fourth quadrant, we take as clockwise, right? So now, as I said earlier, the first type of question, the first type of question that are based on this root locus is whether my point or whether my pole of a transfer function, whether it lies on the root locus or not. Right. So,
एक मिनट है
wait. Okay. So therefore, we have two conditions. Condition number one is angle condition. So in order for any pole to lie on root locus, it has to satisfy angle condition. And what's that? What's that? The angle condition is angle of GH or GSHS. At that pole, let's assume S is equal to S1, it should be 2q plus 1 into 180 degree. So it should be odd multiple of 180, where this q is 0, 1, so right. So in order for any pole to lie on root locus, it has to satisfy this angle condition, right? That is the angle. We will see this how this is solved in examples, but for the time being, just remember, if we have to check whether my system whether my pole lies on the root locus or not, we just have to verify whether it satisfies this angle condition or not. If it satisfies, it lies on the root, it lies on the root locus. If it does not, it does not lie on the root locus. Similarly, then the second part of these questions are, if this point lies on the root locus, then find the value of gain k accordingly. Like with for that point, then find the value of gain k, right? So for that we have another condition that is called magnitude condition. You have read this condition, I'm just revising. So for that, there is magnitude condition, that is magnitude of GH is equal to 1, right? So now let's solve questions based on this. Question number 1. Okay, if GSHS is equal to K divided by S into S plus 4, then test whether S is equal to minus 2 plus J5 lies on the root locus or not. And hence find the value of K. Right? So this is the first type of questions that we see in a root locus diagram. That is, you are given a transfer function, an open loop transfer function, and you're asked whether this pole of it, whether this point S equal to minus 2 plus J5 lies on the root locus or not, right? So what you have to do, I told you we have to satisfy the angle condition. We have to find the angle of this transfer function at this point, and then if that angle comes out to be the odd multiple of 180, then okay, we can conclude yes, it lies on the root locus, otherwise not, right? So we have GS, we have GH given by K divided by S into S plus 4. So we have GH at S is equal to minus 2 plus j5, it will be equal to, just put the value of s as minus 2 plus j5. So it will be minus 2 plus j5 into uh, minus 2 plus j5 plus 4. Right now we have to find the angle, or we can just simplify it a bit. It will be k over minus 2 plus j5 into 2 plus j5. Correct. So now we have to find the angle. I told you. So okay, again, you might have you might be knowing this, that if we have angles for numerator and denominator, and then if we take them Euler's theorem, the angles are subtracted, and you know that. So I'm not going into that. So now angle. So there is nothing in numerator, so 0. Then in denominator, minus, because I'll write them in the, like I'll write angles as such. So minus for the terms in denominator. Then, so if you see this minus 2 plus j5, this term, it lies in second quadrant. So I told you in second quadrant, this real part is negative and imaginary part is positive. So how we should write it? We should write it 180 minus tan inverse of 5 over 2. Correct? So I told you tan inverse of omega by sigma. So without bothering about the signs. So this is in second quadrant. I directly wrote 180 minus tan inverse of 5 over 2. Then they are in multiplication. So I will add, right? So then this, it's in first quadrant. So in first quadrant, it will be tan inverse of 5 over 2. Did I write tan inverse? Yeah. So now simplifying, you can see this and this will go, and we will get angle of GH as minus 180, right? So here should be noted that it should be plus minus. So we are getting this angle of GH as minus 180. So it's indeed satisfied. Angle condition is satisfied. Angle condition is satisfied. It means the point minus 2 plus j5 lies on the root locus. Right. So you just, what you did, you just put the value of that point in the transfer function, then simplified, got the angle, and then checked whether that angle condition is satisfied or not. If it is satisfied, my point is lying on the root locus. If it is not, my point is not lying on the root locus. Now, second thing is, it's given in the question, then also find the value of k. I told you when you are asked to find the value of k, you have to apply the magnitude condition. And what is the magnitude condition? Magnitude of GH is equal to 1. And what is GH? It will be magnitude of k over minus 2 plus j5. I'm just directly putting this value, 2 plus j5. The magnitude of this is equal to 1. So it will be k, then what will be the magnitude of this? Right. So it will be under root of 2 square plus 5 square. It will be 29, right? 25 plus 4. And this was of this, and similarly magnitude of this, again 29, is equal to 1. So it will be k over 29 is equal to 1, implies the value of k is equal to 29. Right? Anybody has any confusion till now? So question number 2 is, let's do it on similar grounds. Show that S is equal to -1 plus minus, not plus minus. Lies on the root locus for g of s, h of s, k divided by s plus 1 into s plus 2 into s plus 4, k greater than 0, and determine the value of k at this point. So now, can you try solving it? Everyone, please try. It's not difficult. Again, we have to first apply the angle condition, and then we have to apply the magnitude condition. Okay, let's try solving this. So GH, it is equal to -1 plus j root 3 is equal to k divided by -1 plus 1 vanishes. So it will be j root 3. Then 2 minus 1, it will be 1 plus j root 3. Then will be 3 plus j root 3. Okay. Now let's take angle of GH. 0 for numerator, then minus for denominator, and this part. This is only positive. Real part is 0. So we can directly write it as. Anybody tell me what will be the angle of this? It will be tan of root 3 over 0, and that is 90 degree. You can directly write it here, 90 degree. Because tan 90 is infinity. Similarly, this is in the first quadrant. This is also in the first quadrant. We can write plus tan inverse of root 3 over 1 plus tan inverse of root 3 over 3. What will be angle of GH? You solve, it will be tan 90 plus 60 plus 30. So it will be 180. So it will be minus 180 again. Okay, so we can see angle condition is satisfied. Angle condition is satisfied. It implies the given point lies on root locus. Now we have found, okay, it lies on the root locus, then we have to find the value of k. So in order for us to find the value of k, we will just use magnitude condition, and our transfer function is this. So it will be k over magnitude of, it will be 3 plus, sorry, into 3 plus 1, 4. 4 3s are 12. 12 plus 3 square is, okay, let me do it for you. It will be 4 3 square into root 3 square plus 1 square into 3 square plus root 3 square is equal to 1. Then it will be k over 3 into 4 into 9 into 3, 12 is equal to 1. 12 fours are 44, 44 into 12 12 is 64. So k is, so it's under root, sorry. So it's whole under root. So k will be, when you multiply, it will be under root of 144, and k will be 12. When we take the magnitude of a plus b is under root of a square plus b square. So that's what I've used here. I'm just recapping. So the first part, the first type of questions that are based on root locus are whether my point lies on the root locus or not. So then for that, you have to check the angle condition. And if angle condition is satisfied, so your point lies on the root locus. And then in order to find the value of k, then you have to use the magnitude condition, that is mod of gh equal to 1, and put in the values, write the magnitude, and you'll get the value of k. Now, without wasting time, let's move forward and directly go towards.
Sir, in this example, I have one doubt.
Yes, yes.
In this example, we have taken 0 minus of 90. Angle?
0 minus of 90, yeah. No. It's all the angles are in first quadrant.
That's why.
Yeah, that's why. So where you have doubt?
This 90 degree.
This? Okay. So this 90 degree is coming from this j root 3. So we can write 0 plus j root 3. So what will be my angle? Tan inverse of root 3 over 0. So tan is infinity. Where is tan infinity?
90 degree.
Yeah, that's why. You can take a tan inverse of tan of this, tan got cancelled, and you'll get 90 degree. Is that clear?
Yes.
So now let's move somebody. Yeah. So now let's move towards the construction of root locus. There are certain rules which we need to follow. So I'll quickly like revise you those rules. You might have gone through them in your lectures, but yeah, still I'll just recap those. Just remember these rules, because when we draw the root locus, it will be very important. So first rule is, or I'll just say it. I'll just write it. Root locus is symmetrical about real axis. What is real axis here? Sigma. So for example, if you have complex poles, you know that complex poles occur in pairs. So if any one of the pair lies in root locus, then automatically the other pair as well lies on the root locus, because this root locus is symmetrical about real axis, right? So now rule number 2 Rule number 2, let's assume P is the number of poles of an open loop transfer function, which is generally given as GH HS. So here, if you notice, when we studied routes criteria, there I was interested in the closed loop transfer function. I often said, okay, then you have to take the closed loop transfer function, find the poles, then judge, okay, if the poles are in the left half, my system is stable, otherwise not. But here we are seeing the open loop transfer function, and based on open loop transfer function, we are able to decide on the closed loop poles, right? So this is very, very important. So you, in root locus, you're only using open loop transfer function and getting the results, or what you were able to decide in routes criteria from closed loop transfer function. Here we are, that work is being done from the open loop transfer function. So this is very important. So let P is the number of poles and Z is the number of zeros. And normally, in most of the cases or in practice, you often have proper transfer function, that is, the numerator has less degree than the denominator. So you will have more poles than zeros. That has a reason. So because those only those transfer functions are realizable, and you might have studied that, or you will just go through that. But what you have to remember is that in practice, or most of the time, or in almost every question, you will get your poles, number of poles will be greater than the number of zeros, because that makes the transfer function proper, and that's why then it becomes realizable in the practice. And even mathematically, it's possible that we can make zeros greater than poles. Then the root locus, slightly other rules, or you have to be very careful while drawing it. But in your syllabus, mostly you'll get transfer functions where the number of poles are either equal to number of zeros or they are greater than the number of zeros. So then, so what I said, P is greater than Z. So then the number of, and then it's a number of branches of root locus is equal to P. So the number of poles, they give the number of branches in a root locus. And very, very important point, a root locus starts from a pole and terminates at a zero, right? So for example, okay, I'll come to that. But as of now, the number of branches of a root locus, they're equal to the number of P. And what I said, each branch in a root locus will originate at pole and terminate at zero. Right, so while drawing root locus, you have to be very careful about this point. So, and the number of branches will be P, and okay, let's assume I have P number of poles and Z number of zeros, and P is greater than Z, or in particular, let's assume I have 3 poles, 2 zeros, right? So then what I have, P minus Z is 1. So I said that my root locus starts from a pole and terminates at a zero. So I have 3 poles, out of which two branches will terminate at zero, but there is still one left. There is still one branch left, and that terminates at infinity, right? Because yes. Because we can say that infinity is the virtual zero. So this P minus Z branches, they terminate at infinity. So if you have a scenario where the number of poles is greater than the number of zeros, if the number of poles are equal to the number of zeros, then no problem, right? The poles will terminate at zeros. But if you have a number of poles greater than the number of zeros, then the number of poles then the number of branches, that is P minus Z, they will terminate at infinity by treating infinity as a virtual zero, because if you put infinity in the transfer function, that will also give you a zero value. So you can treat it like that. Okay, so another rule is, another very, very important rule is points on real axis belong to root locus if and only if right of the point, right of that point odd number of poles and zeros lie, or in other words, I can say uh, a region in real axis that belongs to the root locus, if to the right of that region the sum of the poles and zeros is an odd number, then that region lies in the root locus. We'll see it with the help of an example that will be more clear. GH is given by K into S plus 2 into S plus 6 divided by S into S plus 4 into S plus 8. Okay, so now here we can see number of poles P is equal to 3, number of zeros is equal to 2, and poles are 0, minus 4, minus 8, and zeros are minus 2 and minus 6. Now let's visualize it in the S plane. This is sigma, this is j omega. This is my pole at 0. This is my pole at 4, minus 4. This is my pole at minus 8. Right, so I'll make zeros. Now this is my 0. This is my 0 at minus 2. This is my 0 at minus 6. Okay, so I told you first point is root locus. It starts from a pole and it originates from a pole and terminates at 0. So, and second thing is, I right now told you a region belongs to the root locus if to the right of that the sum of the poles and zeros is an odd number. So for example, let's see whether this region lies in the root locus or not. If we see this minus 2 is a 0, and to the right of this minus 2 only one pole lies, and pole is an odd number, therefore this region lies in the root locus. Now again, I told you a root locus always starts from a pole and terminates at a 0, so it will be like this. Okay, so the direction of root locus will be it starts from a 0 pole and terminates at the origin. Now let's see this region, right? So this region, so if we consider this region, you can see there are two there is one pole and one zero. So this region will not be in the root locus, because to the right of this region there is one pole and one zero, so it's a even number, so it doesn't lie on the root locus. Now let's consider this region. So in this region we have two poles and one zero. It's an odd number, so again it does lie on the root locus, and it will start from pole and it will terminate at 0. Right. Similarly, this region will not lie on the root locus because we have 4 as the number of poles plus number of zeros. Then again, this region will lie and here it's minus infinity. So you can say it goes like this, right? So let me make it a bit better. So we can see we had 3 poles and 2 zeros, and 2 poles they terminated at zeros, but 1 pole -8 it terminated at minus infinity. So as of now, what we have learned, uh, the number of branches are given by the number of poles, mostly because p is greater than z in our cases. Then uh, p minus z branches terminate at infinity, and for our region on real axis to be to lie on the root locus, it has to satisfy this property that to the right of that pole or zero, and the sum of poles and zeros should be an odd number. Right now, as I said, that p minus z branches, they uh, converge at infinity, like they converge to a zero, and that zero is treated as a virtual zero, and so that goes to infinity along an asymptote, right? So that goes to zero along an asymptote, and the angle of which is given by, so the number of branches given by p minus z, they terminate at infinity, and how they go to infinity, they go infinity along asymptotes, the angle of which is given by, so angle of asymptotes. Theta, let theta be the angle of asymptotes. It's given by 2q plus 1 into 180 degree divided by p minus z, where q is equal to 0, 1, so on up to p minus z minus 1. Okay, so this is the angle of asymptotes. That is how those poles given by p minus z go to infinity. Like they go along infinity, they go to infinity along these asymptotes, and the angle of which, and the angle is given by this formula. Right now, the intersection of these asymptotes on the real axis is called centroid, and the centroid is given by the form.
Sir, I have one query, sir.
Yeah.
Sir, in question it is given that the real part of the root locus branches going to infinity would converge to.
Yes.
So what is the meaning of this, sir? The real part of the root locus branches going to infinity would converge to.
It's in questions given.
Yes, question is given, sir, in
So
assignment.
okay. I will come to that. So give me some minutes. I'll just finish those rules. When we do one question, everything will be clear.
Okay, thank you.
Right. So as of now, you just remember that the branches, they start from poles and they have to terminate at 0, right? And when the number of branches, when the number of poles is greater than the number of zeros, then there will be some branches which cannot terminate at 0, and in that case they have to terminate at infinity, right?
Yes, sir.
So in that case, we sometimes use the terminology of converge, because from infinity, where will that go?
They will
Right.
converge.
Yeah, so we will come to that. We'll solve problems.
Okay.
But as of now, as of now, so this centroid is the intersection of all these asymptotes on real axis, and this is given by sigma. That's equal to summation of real part of open loop poles minus summation of real part of open loop zeros divided by E minus Z. So do you all know these things? Do you want me to revise, or we can directly go to questions?
Yes, yes. We can directly go to the question.
Anybody else wants me to revise these things first? Like, yeah, please. So then we can directly go to questions, because I assume if you know breakpoints, if you know centroid, asymptotes, angle of asymptotes, and whether it be a break-in point or breakaway point, then we can directly start from questions. Or I can explain those things in the questions. That will be, I think, more better. Okay, let's do one thing. Let's solve this question. Then we'll get to know. If anybody has any doubt, then I can revise or recap. Otherwise, if it's okay, then we can just solve the questions. So we have a question that is plot root locus of a unity feedback system whose fourth part transfer function g of s is given by k divided by s into s plus 2. Correct? So what will be characteristic equation here? So let's assume we do not know root locus. So what will be characteristic equation here?
1 plus this k over.
Yeah. So my characteristic equation will be s square plus 2s plus k equal to 0. Correct? So in this case, I clearly know that I have two roots. Right? Now, if k is equal to 1, then I have s square plus 2s plus 1. It implies I have s plus 1 whole square equal to 0. It means, what do I have? What do I have? I have repeated roots, right? So if you know, when we have repeated roots, then we may have a breakaway or a break-in point. Is that clear? Or I'll explain. So in that case, I should have a repeated root. This is one way of checking. Other way is to see directly from the root locus. You can also like see it from there. So okay, as of now, what do we do in root locus? We just vary the gain k and see the locus of our closed loop poles. So whenever there is at some values of k, whenever there are repeated roots, then there is a breakaway or a break-in point. That is, our branches, they collide, right? So okay, I'll come to that. But as of now, let's try to solve this question. So and draw the root locus. So we have two poles. So pole is at 0 and -2, right? And we have no 0. Correct? So, okay, wait. Okay, so we have no zeros. So what will be, so we have two poles and no zeros. So both the poles will converge at infinity, because there are no poles, no zeros. So both poles will converge at infinity, right? And I again told you, so what is P minus Z? P minus Z is 2 minus 0, that is 2. right? So both poles will converge at infinity, and I told you, but they go to infinity along certain straight lines which are called asymptotes, and the angle of which is given by the formula. So we'll calculate θ1 and θ2. So θ1 is 2 into 0 plus, what's the formula? Plus 1 into 180 plus 1 into 180 divided by 2. So that will be 180 over 2, that will be 90 degree, and θ2 will be, when you take 2 on 1 into 3 divided by 2, it will be 270 degree. Correct? So we have θ1 is 90 degree, θ2 is 270 degree. Whenever you have P minus Z as 2, no need to calculate. You'll always get 90 degree and 270 degree. Right? So if I plot it here, so this is 90, this is 180, and this is 270. Right? So this is 270, this is 270. But I can say this 270 as minus 90 as well. Right? So I can say it minus 90 if I am taking the angle clockwise. If it is counterclockwise, then it will be 270. But if it is clockwise, then it will be minus 90. So whenever you have P minus Z as minus 2, this P minus Z as 2, then the angle of asymptotes will be, you no need to calculate, just directly write θ as 90 and θ2 as minus 90 or 270, one and the same thing. Right? So, okay, you have found, let's try to plot. So you have two poles, one is at 0 and other is at minus 2. This is minus 2. And then I told you they will converge at infinity, but how they will go to infinity, that's very important. Right. So then I told you to find the asymptotes, angle of asymptotes, and then what now, where is the intersection of asymptotes? So we need to find the centroid as well. So what is centroid? Centroid is sigma, that is given by summation of real part of poles, summation of a real part of open loop poles, that will be 0 minus 2 minus summation of real part of 0, that is 0, divided by P minus Z, that is 2. So my centroid will be minus 1. Right? So the intersection of these asymptotes on the real axis will be minus 1, 0. So it will be somewhere here. So this is my centroid. Now I told you the angle with which these branches will go to infinity will be given by these asymptotes. So I'll draw these asymptotes. These are my asymptotes. This is my 90 degree asymptote. And again, this is my 270 degree asymptote. Correct? So it's in other words, it's plus minus 90. Right? So I draw asymptotes, and the point at which they intersect the real axis is given by centroid, which is minus 1. Right? So now you see my root locus, it will start like this, and it will start like this. Now, why I started like this? Because if you see this region from minus 2 to 0, that region should lie in the root locus. Why? Because the number of poles or zeros to the right of minus 2 is odd. So that automatically, so this region comes in the root locus. Now this region, if we see, we have two poles towards the right of this region. So it's an even number. So it cannot be the part of root locus. The only part of root locus is the region between minus 2 and 0. Now you can see this minus 2 and 0, they are approaching towards each other. So whenever you have a scenario like this, like your root locus is between two poles. So whenever your root locus is between two poles, so then there is a breakaway point. right? So these branches, they are coming, striking each other, and they will break away, right? So whenever you have to remember, that's why I told. So I'm assuming if you know these things, then we can directly solve the question, right? So whenever you have the part of root locus, or whenever you have the branches of root locus between two poles, then there will be a breakaway point. Or similarly, whenever you have branches of root locus between two adjacent zeros, then there will be a break-in point. They will converge together, right? So, and why this breakaway point occurs or break-in point occurs? It occurs because when we vary gain k, at some values of k, we get repeated roots. On that point, we get repeated roots. That's why I initially solved this problem like this. That's why I had solved it. If I put k equal to 1, I get s plus 1 equal to 0. It means I get repeated roots at s equal to minus 1. So I know at s equal to minus 1, I get repeated roots. But this was very simple for me to solve. So it was a quadratic equation. What if I have a fifth order or sixth order equation and I need to solve whether I have a break-in point or breakaway point or whatever? So in that case, what we do, like how we find this break-in point or breakaway point. So what we do, we write characteristic equation, right? So in our case, characteristic equation 1 plus gs equal to 0, and that will be s square plus 2s plus k equal to 0. So whatever order your transfer function is, you can always write a characteristic equation. Then this characteristic equation, you have to write in terms of s. So you have to write k, you have to decouple k from this characteristic equation. So we can write it as k equal to minus of s square plus 2s, right? Or minus s square minus 2s. Then what you have to do in order to find break-in or breakaway point or break point in general, then you have to differentiate it with respect to s. So dk over ds is equal to minus of 2s plus 2, and this you have to put to 0. It implies 2s plus 2 equal to 0, s is equal to minus 1. Right. So my breakaway point, because I know there will be a breakaway point. Why? Because my root locus is between, the branches are between two adjacent zeros. So whenever the branches are between two adjacent zeros, it will be a breakaway point. And where that breakaway point will be, it will be at minus 1. It will be at minus 1. But coincidentally, this minus 1 is also our centroid. This minus 1 is also our centroid. I told centroid is the intersection of all the asymptotes on the real axis, and centroid is our like minus 1 is our centroid, and minus 1 is our breakaway point as well. So we will see examples where centroid is different, our breakaway point is different, right? So we'll see every scenario here. So now what will happen when these branches reach minus 1, then they break away to infinity. And how they will go to infinity? They will go to infinity along asymptotes of angle 90 as well as of angle 270, right? So one pole will go like this and other pole will go like this. Okay, because this was 90, this was 270, sorry, or minus 90 or 270. Minus 90.
How you get the theta to 270?
How I draw? See.
Theta to 270 degrees.
How I got this?
Yes, sir.
So my angle of asymptotes is 2q plus 1 into 180 divided by p minus z. So I will put q equal to 0, 1, and so on up to p minus z minus 1. So my p minus z here is 2. So minus 1 is 1. So I will put the value of q2 up to 1, 0 and 1. So when I put the value of q as 0, I got 90. And now if you see theta 2, it will be 2 into 1 plus 1 into 180 divided by p minus z is 2, right? So 2 plus 1 is 3, 3 into 180. So it's 3 into 180 divided by 2. It's 2, 290, 9 threes are 27, 270. Is that clear?
Yes, sir. And characteristic equation, sir.
Uh-huh.
Square
How I wrote that?
Yes, sir.
Okay. Okay. So see, given I have GS is equal to K divided by S into S plus 2. But I have been given it's a unity feedback. What will be H of S? It will be 1. It will be 1. So if my H of S is 1, G of S is given by this. I know my characteristic equation is what? 1 plus G of S H of S. So it will be 1 plus K divided by S into S plus 2 into 1, right? And if I this put to 0, so what will be this? It will be, I need to multiply this, and this equal to 0. So it will be S into S plus 2 plus K divided by S into S plus 2 equal to 0. So it will be S square plus 2S plus K equal to, this will go to 0. It will be 0. This will be my characteristic equation. Is this
Thanks.
fine?
Thanks, sir.
Yeah. Okay, so that's why I was saying, so it's better to revise first and then do the questions, because for some it will be easier, because revision is sometimes very important. Then that's the way that things will become more clearer. Okay, anyway, so here for this specific question, what we had this centroid as well as the breakaway point. We had the same. We had they were both at -1, so we had same point. So we can write one thing. Maybe we'll have the same thing in some other question as well. When centroid and breakpoint. So breakpoint can be breakaway or break-in. Breakpoint coincide. Branches break along asymptotes. You see here, I did not do anything fancy like this or this. I just like sent them to infinity through asymptotes. We'll see in other questions. We will see in other questions that how like this point will be more clear in other questions. Now, one more important thing is, again, I told you that there will be a breakaway point when the root locus lies between two adjacent poles. There will be a break-in point when the root locus lies between two adjacent zeros. Two things you remember, that is, adding a pole to a system shifts the root locus towards right and makes the system unstable. So, or in other words, we can say it reduces the system stability. You can just try it. You can just take a random transfer function and just add a pole to it, and then see the response, the overall response. You will see the root locus is shifted towards the right. So if it crosses the imaginary axis, then your system will be unstable. Similarly, if you add a 0 to a system, that shifts the root locus to the left. So it improves the stability. It increases the stability, right? So you may see stuff on this. And one more thing is, sometimes you are being asked to find the intersection of the root locus with the imaginary axis. So how you do that? So that is directly given from the like routes criteria. So you just have to find the auxiliary equation, and the roots of auxiliary equation will give you the intersection. We'll check that as well in the questions. And now the last thing, then after that we'll directly go to the question. I'll just revise. what is angle of departure and what is angle of arrival, right? So if you see here, we had only two poles and both poles were real, right? So my pole can either move in this direction or this direction. There are only two directions. Either it's 0 degree or it's 90 degree, 180 degree. There are only two directions. In case of a real pole, there are only two directions. Either it will move towards in 0 degree direction or minus 180 degree or 180 degree direction. But if we have a complex pole, then it will be somewhere here or somewhere here. And this complex pole has n number of directions to move. For example, if it is a complex 0, or if it is a complex pole, then it will start from this complex pole and converge to some complex 0. And how it will leave this complex pole, at which angle it will leave, that is called the angle of departure. So whenever we have a complex pole or a complex 0, so we can have angle of departure or angle of, I'll just write it for you. Because it's otherwise very complicated. At any complex pole or 0, there can be infinite directions. There can be for any branch to leave or enter, right? Then angle at which root locus departs from a complex pole, this is called as angle of departure. Similarly, angle at which root locus arrives at a complex 0, this is called angle of arrival. Now there are formulas for this angle of departure and angle of arrival. So phi d is angle of departure. It's given by 180 plus angle of gh dash, and phi a is the formula for angle of arrival, which is given by 180 minus angle of gh dash. And how this angle of gh dash is calculated, right? So where gh dash is the transfer function obtained by removing that part of complex pole or 0 at which the angle of departure or arrival is calculated. Right? So it may be confusing, but we'll do some questions and it will be very easy. So in general, what you have to remember, that sometimes you cannot have only real poles or real zeros. You can have complex poles or complex zeros as well. And when you have complex poles or complex zeros, then the root locus can leave or enter in n number of angles, in n number of ways. And the angle at which that root locus leaves, if it is a complex pole, that's called angle of departure. And if it is a complex 0, the angle at which the root locus arrives on that angle is called angle of arrival, right? And these are given by this formula, if you have to calculate angle of departure and angle of arrival, it's given by 180 plus angle of the transfer function obtained by removing that pole or zero at which the direction of or the angle of arrival or departure is calculated. Correct. So now let's solve one problem. Let's solve one problem on this, and then we'll be more clear. For example, question: if GH is given by K divided by S plus 1, S plus 2 minus J, S plus 2 plus J, K is greater than 0. So we have to determine the angle of departure. So if it is angle of departure, then it will be for a complex pole because there is no complex zero. So we have to find phi d for the pole at S equal to minus 2 plus J, right? So we have to find the angle of departure for the pole at S equal to minus 2 plus J. So we have two poles. One is at one is at minus 2 minus J, other is at minus 2 plus J. So we have to find at one pole, or in other words, if we plot this, we have one pole at minus 1 and other pole at minus 2 plus J here and here. So we have three poles in general, two complex and one real. So we have to find the angle of departure from this pole, right? So what I told you. So I'll apply the formula. Phi d is equal to 180 plus angle of GH dash. And what is GH dash? So GH dash is the transfer function obtained by removing that particular pole at which it's calculated. So in that case, it is minus 2 plus J. So it will be this one. This one is removed, because if you take this, so it is S plus 2 minus J, or it implies S is minus 2 plus J. So this part is removed, and then the transfer function we get is the GH dash. So the GH dash will be K divided by S plus 1 into S plus 2 plus J. Correct? So this is GH dash. Now we have to find the angle of GH dash. Okay, angle of GH dash again. So numerator, nothing is there, 0. Then denominator minus. Now this is sorry, you have to put one step is you have to put S is equal to minus 2 plus J. Minus 2 plus J. Right, so you have to put this value. Then what we will get? We will get K divided by minus 2 plus J plus 1 into minus 2 plus J plus 2 plus J. So this and this will go. You will get K divided by minus 1 plus J into this will be 2J. Right now, clearly angle, now we have to calculate. So angle of GH dash, 0 for numerator, negative for denominator. Now this is in the second quadrant. I can directly write it 180 minus tan inverse of 1 over 1. Then multiply means plus. Then we have 2J directly, as I wrote earlier, 90 degree. So what will it be? It will be 0 minus, this is 45. So it is 180 degree minus 45 plus 90. So what will it be? it will be 180 plus 90 is 260. 260 minus 45 is 225. Right? So it is 225 minus 225 degree. So angle of GH dash is minus 225 degree. Right? Then we can find the angle of departure, that is 180 plus angle of GH dash, which is equal to 180 minus 225, which is equal to minus 45 degree. Right? So what does it mean? What does it mean? It means at this pole, this root locus will leave, this is clockwise. So clockwise 45 degree, right? So it will leave in this direction. So at this pole, this root locus will leave in this direction. So is this clear? So it's clockwise, so it's minus. Or in other words, I can write it 360 minus 45. In this way, I can draw it like this. So be very careful. If you are asked to find the direction in counterclockwise direction sometimes, then you have to like write that accordingly. Right? So it's minus 45 means you can draw it like this as well, or it will be 360 minus 45. So I hope this is clear. So this is how you find the angle of departure and angle of arrival for a particular complex pole or a complex zero. Right? Anybody has any question or wants me to repeat or just summarize it again? I'll do that. Because now we are going to do a question which will clear all your concepts. That will have everything. Or before that, can you find, okay, yeah, it will be a good task. You're given GH K into S plus 1 plus J, S plus 1 minus J divided by S into S plus 2J, S minus 2J. Now, can you find the angle of departure for the complex pole at S is equal to 2J? So can you try? Everybody, please try. So I'll give you a hint. So 2J means this will not be considered in the GH dash transfer function. So I'll give you some hints. So angle of departure we need to calculate. So that will be 180 plus angle of GH dash. So GH dash, first of all, you need to find. So you need GH dash is a transfer function which is made by not considering the pole at which the angle is calculated. So we'll write everything. It will be K into S plus 1 plus J into S plus 1 minus J divided by S into S plus 2J. Then this part will not be considered. S equal to 2J. Now this GH dash at S equal to 2J is given by K two J plus 1 plus J, 2J plus 1 minus J divided by 2J into 2J plus 2J. Is that okay? So just simplifying it a bit, it will be K into.
Sir, one more term is there in denominator. S minus.
Yeah, what I said. We are making this GH dash such that the pole at which the angle is calculated is ignored. That's what we did here. There were three terms. There were three terms in the denominator. When we made GH dash, we only considered two.
Okay, sir.
Okay, so it will be 1 plus 3j, and then it will be 1 plus j divided by 2j into 4j. Correct? So now if you have understood, you can easily find the angle of GH dash. That will be equal to tan inverse of 3/1 plus tan inverse of 1/1 minus 90 degree minus 90 degree. Right, so this tan inverse of 3/1, it is 71.56 degree plus 45 degree minus 90 degree minus 90 degree, which is equal to minus 63.4 degree. Therefore, phi of d will be equal to 180 minus 63.4 degree, which is equal to 116.6 degree. Is that clear? Anybody has any doubt, please do not hesitate to ask, because this is very important. Otherwise, you'll not be solving any assignment question. I'll again come to assignment questions as well. We have some practice assignment problems. I'll see whether you can solve them or not. Yeah, I think we are now able to solve these assignment problems. We should be able to solve.
So we can consider any angle of any pole as an angle of departure.
No. Yeah, any pole. Now there is one more thing. One more term is there. So if I told you by rule number 1, root locus is symmetrical towards the real axis. So if it is, the complex poles occur in pairs. So if it is this 116 degree here, then on the other pole, that is s plus 2j, which will be s at minus 2j, it will be minus of 116 degree, right? So it will be conjugate of it. But yeah, you can, the crux is you can calculate angle of departure for any pole, be it real or complex. But for real, you know that there are only 2 ways to go. So that's why we mainly calculate it for complex poles and complex zeros. Yes.
Yes, thank you.
So there is one question in practice assignment. We'll solve this first, and then we'll solve one question which will clear your doubts. And I don't think we can solve some good questions, but I'll try to finish it, like try to cover as many questions as I can. So it's given, consider the open loop system with unity feedback given by 2k into s plus 5 divided by s into s plus 13 into s plus 2. At least if we do not solve this question fully, but we should be able to know that how this can be solved. So the question is, the root locus plot with k being varied from 0 to infinity. Now, first question is, how many branches does the root locus have? Now tell me, you should be able to answer this question. How many branches the root locus has?
How many
Yes.
branches?
3.
The root locus has?
3, sir.
Yes, 3. 3. Why? Because I told you the number of branches are given by the number of poles. So done, no need to write. Now tell me, how many poles do we have? We have only one pole. So p minus z is 2. So 2 branches will go to infinity, will converge at infinity, correct? But they will go to infinity through asymptotes, the angle of which is given by some formula. So I told you, when p minus z is 2, what will be the angle of asymptotes? Theta 1 and theta 2?
90 and 270 degree.
90 and 270. So the second number question is, uh, uh, you have to find the angle of asymptotes. So done. Very simple. So, but if you now see, if we try to plot the root locus, sigma j omega. So we have three poles. One is at 0, other is at 2, then we have one at 13, minus 13, minus 2, and 0. And we have one pole which is at 5, minus 5. Correct? So now tell me which region, this region, is it, will it come in root locus, this region?
Yes, sir.
Definitely it will come, because to the right of minus 2, there is only 1 0, and which is even, so this will come. So, okay, this will come. I will just include it like this as of now. Now tell me this region, will this be a part of root locus?
No, sir.
No.
No, because we have an odd number of poles and zeros. And this region?
Yes.
Yes.
Yes, it will be a part of root locus. Correct. Now tell me one thing. There is one question in your practice assignment for the same problem. The question is, does s equal to minus 4 lie on the root locus?
No.
Yeah, the answer is no. So as simple as this. So you have only simple questions in your assignment, but once the things are very clear, you won't take much time to solve them. So this is one question, that does s equal to minus 4 lie on this root locus? No. One way of doing this is directly by seeing on the root locus a probable plot, you know that which part will be which region will be a part of root locus, so you can directly answer. Right. Now another question is, you have to find the centroid. So you know there will be two asymptotes. The two asymptotes will intersect at real axis. So you have to find the centroid. So how do we find the centroid? Centroid is very simple. Summation of real part of poles minus summation of real part of zeros divided by p minus z. So centroid, I'll write centroid. Let's assume sigma is the centroid. It is summation of real part of poles, that is 0, minus 2, minus 13, minus summation of real part of zeros, minus 5, divided by p minus z, that is 2. It will be 12 plus 2 plus 13 is 15, 15 plus 5 is 20. No, minus plus 10, 10 over 2 is 5. So centroid is 5. So my centroid is, this is my centroid here. Now you know one thing, that my asymptotes will intersect at this centroid. I'll just make these. Right, so these are my two centroids at minus 5. Now, I told you, whenever root locus lies between two adjacent zeros, what happens? Between two poles, what happens? There, a breakaway point will come, right? For example, but you don't know that breakaway point. So how we calculate that breakaway point? We write the characteristic equation in terms of k, then we differentiate k, and then we solve for s, and then I'll do that. So what is the characteristic equation? So the characteristic equation can be written as, I'll just write it in terms of k directly, because then we can solve more problems. So it will be minus of s cube plus 15s square plus 26s divided by 2 into s plus 5, right? Okay, then if you differentiate this dk over ds, you can use the division rule of differentiation, and when you solve this, put this 0, you will get s cube plus 15s square plus 75s plus 65 equal to 0. At least I'm giving you an idea. Then you can confirm these things later on. And if you solve S, what you will get the value? The value will be minus 1.085, comma, minus 6.96 plus minus J 3.39. Now come to the root locus. Let's analyze this part first. Is this the part of root locus? This minus 6. As of now, I said the breakaway point will be where? It will be between
0 and minus 2.
Yeah, between two adjacent poles. So between minus 2 and 0, we can see this minus 1.085 it lies. So we can write, for example, it here. So breakaway point is minus 1.085. So at this point, these poles will break. So this is very important. You have to be very careful what I'll do here. So for example, now my poles were coming along this direction and here along this. When they reach this point, they will break, right? They will start breaking. And where they have to go? They have to go to infinity. But how they have to go to infinity? They have to go to infinity along the asymptotes, right? So they have to go to infinity along these asymptotes. So it will be like this. Right? So I didn't draw it like correctly, but you should get an idea. So now they will go to infinity along this direction. Similarly, they will go to infinity along this direction. Right? So this is how the root locus will be like. You can draw this root locus using MATLAB and Simulink for the same transfer function, MATLAB, and then you'll get an idea like how this root locus will look like. But the basic idea is this. So you have a breakaway point, and when you have a breakaway point, then your branches, they need to go to infinity along asymptotes. So that's why I earlier said, whenever your centroid and asymptote, whenever your centroid and breakaway point are same, then you just have to draw these branches will go to infinity just through asymptotes. But now you have different breakaway point, different centroid. So now your branches will break at this breakaway point and then go to infinity through the asymptotes. And this region is also a part of root locus, but it will terminate at -5 because -5 is a 0 of this transfer function. Is this clear? Is this clear? Any question like till now? Or again, I'll touch one more important part. Touch one more important part, that is sometimes you get a circle in root locus diagram. So when do you get a circle in root locus diagram, and what you do in that case? Right, we'll solve a problem on that as well. So whenever you have a transfer function, open loop transfer function like this, k into, remember this is very, very important questions perspective, or maybe you'll be asked, or maybe there will be some question in the assignment as well on this. And you are given b is greater than a. So if we need to plot this, so what we will get? This is sigma, this is j omega. So we have two poles, one is at 0 and other is at a, and we are being told that b is greater than a, so b will be somewhere here. B is 0. So b is 0, so minus b. Correct? So in this case, we can see this region is a valid region for root locus, but this region is not. Again, this region is a valid region for root locus, right? This region. Is this okay? Because we can assume, okay, one more thing, we have two poles, one zeros. So one one of my branch will terminate at B, other branch will terminate at infinity, correct? But can we do it like, can we think it like this? So I told you one of my branches is at infinity, one of my zeros is at infinity. So this region is a valid region for root locus, or we can say, I told you that whenever there is a region between two poles, then there will be a breakaway point, and whenever there is a region between two zeros, there will be a break-in point. So there are two poles, minus A and 0. So there will be a breakaway point here, and there are two zeros, minus infinity and minus B. There will be a break-in point here. So my root locus will look something like this. It will be a circle. So it will be, so this is, root locus will come like this, then it will come like this. Similarly, my root locus will go like this. Sorry, no. Because it comes towards 0. It terminates at 0, something like this. So my root locus, this is my breakaway point. Let's assume this is my break-in point. Wait. Okay, let it be.
Sir, I have one query. Sir, if the range of K for this shape is obtained as A, comma B suppose, then value of B is, we have to take this minus B.
So you mean at place of A, we have B, and at place of B, we have A, right?
Yes, yes.
But in that case, you will not have breakaway point or break-in point.
Yes, yes.
This is a particular case. When you have your root locus between two adjacent poles, you have a breakaway point. So my breakaway point, it will be something like this. So it will break like this. But then it will again here come back and originate here. So you'll get a circle. Definitely root locus, the shape will be circle. But now what will be the center of this circle? Now the center of this circle is given by, there's a full derivation, but just remember B comma 0 and radius is given by under root B square minus AB. There are many ways you can imply this. See, for example, you know this minus B is the center. You also know that breakaway point and break-in point, they lie on the boundary. So this, if this is center, then this region towards the breakaway point, because breakaway point you can easily calculate, or break-in point you can easily calculate. So you know the value of B because B is the 0, open loop 0. So you know the value of B, you know the value of breakaway point. You can directly find the difference, and that will be the radius. So think it like that.
Sir, how we can find maximum overshoot in this case like this?
Maximum overshoot?
Yes, sir.
Why do we need to find maximum overshoot?
It is there, sir, in assignment question is there. The value of K for which the system has maximum overshoot.
Okay, so there are two ways. One is the value of K when K, the value whenever, so in route Howard's criteria, what you do, you find the value of K for which there is no sign change. And if all my poles, there is no sign change, then the system is stable, right? But for some cases, there will be marginal stability, right? So the marginal stability case means when my root locus intersects imaginary axis, or my value of that row, let's assume S1 in that case is 0. My row, if I have row of zeros, then we saw in the earlier class that we get marginal stability, and after that, and if K is not in that region, we get an unstable system, right? So exactly what is the question? I don't know. Like if it is marginal, stable, or stable overshoot, I do not know. Maybe it's because of you need to find damping or something. I
Sir,
think
whether you
there's
have
a
to find
relationship.
overshoot by the MATLAB, sir? Maximum
Whether
overshoot.
you want to. No, no, yeah. I got it now. There is this relation of gamma. So when my system will be overdamped or underdamped or critically damped. So if it is overdamped, my gamma is less than one. Greater than one. If it is underdamped, my gamma is less than one. Gamma, sorry, zeta. So do you recall that? In second order systems, if you have, this is the second order, uh, this characteristic equation, 2 zeta omega n s plus omega n square. This is zeta, this is the damping ratio. So if zeta is greater than 0, we have overdamped system. So in that case, the response will be like this. Or if my zeta is equal to 1, it will be critically damped. The response is this. If my zeta is less than 1, then it will be overdamped. The response will be like this. So the maximum overshoot will be when my zeta is less than 1. Right. So it means there is a relation. Yeah, there is one type of questions where you are asked to find the damping ratio, because any point on this root locus is a complex point. When you join that, you will get some angle, and then that angle is given by theta, and that theta is given by, I don't remember exactly, I'll have to check, but that theta is given by cos of gamma. This gamma is the damping ratio. Theta, you'll get the damping ratio. So if your damping ratio is greater than 1, less than 1, or whatever, or you can decide when my theta is less than 1, what should be the value of my angle, and accordingly you can decide, okay, this should be the conditions. You just check it. This similar type of condition, there will be where there will be the relationship between damping ratio gamma and the theta angle. Then maybe you can decide.
Sir, when these open loop poles are there, their K is 0.
No, like open loop zeros are there. Well, I don't understand. What do you mean
This
to say?
circle, from this circle, suppose
Mhm.
when you start from open loop poles, at open loop poles, value of K is 0, na, sir?
At open loop pole, you mean at B, when my root locus is at B?
Yes, when root locus starts at open loop pole, value of K is 0. And as you go from open loop poles to open loop 0, the value of K
Okay.
increases.
Wait. Okay, I understood. See, I told you that in root locus, what we do, we give the characteristics of a closed loop system in terms of open loop poles. Sorry, open loop poles and zeros, correct? So I
Yes.
told you in root locus, we only need G of S, H of S, but in Routh-Hurwitz criteria or whatever we studied till now, we needed 1 plus GSHS, correct? And I again said, my root locus, it starts from a zero, my root locus, it starts from a pole and it terminates at a
0.
zero. So I said, what is root locus? Root locus is I need to vary K from 0 to infinity. So when my root k is 0 and I vary this k from 0 to infinity, I get a root locus. So eventually, when my k is infinity, I should be at an open loop 0. And when my k is 0, I should be at open loop pole. Is that what you want to say?
Yes. But my question is that, sir, in circle, where it will be the maximum overshoot? It is
In
not.
circle,
It
So
cannot be
can you
detected.
tell me, would you be able
Because
to
there is a
find maximum
question in
overshoot?
assignment, sir. We got also one circle,
Okay.
and they have asked the question: the value of K for which the system has maximum overshoot.
Okay, that's what I said. So that question is not related to this question.
Okay.
Right. I said that question, for that you just check this relationship. I do not remember that exactly, or I'll have to check. Just give me 1 second. So are there any questions where you are being asked to find the value of K where you have a damping ratio of this something?
No, in assignment there is a question, sir.
Only one question.
No, one block diagram is there, and
Okay.
from that the root locus is plotted by varying gain in the range of 0 to infinity,
True.
and the shape of
True.
root locus for a particular range of k. It is a circle where I am getting
Okay.
circle,
Okay.
and if the range of k for which the above shape is obtained वो पूछा है, और उसके बाद में वैल्यू ऑफ के फॉर विच द सिस्टम हैज मैक्सिमम ओवरशूट.
Okay.
It will be rounded 2 decimal places.
That's fine. That's fine. Okay, I think you should like be able to do that with the help of this formula, because overshoot, I can tell you the value of K for which my system is marginally stable or asymptotically stable, that we can get from root locus. But if you have to find the overshoot, then overshoot has a formula. The formula of overshoot is, I think,
MP is equal to e raised to power minus pi zeta.
Yeah. And that, what is that? Pi and 1 minus
E raised to power
zeta
minus
square.
pi zeta by square root of 1 minus zeta square.
Yeah, this formula, what I wrote.
Yes.
Yeah, so that's why what I said. So this, you have this damping ratio. You can find this damping ratio. You just check it. There will be a formula, and we are being asked. So whatever question they are in the assignment, we only have to give hints before the after the due date. So maybe in the next lecture I'll solve that problem. But as of now, we can only give you hints, and the hint is, probably there is this relationship, this theta, any point or any angle, we can write in terms of damping ratio. And if you are able to find the damping ratio, then you should be able to find this overshoot, and you can easily find when my overshoot should be maximum using
Yes,
that.
sir.
So I think this is the proper way to tackle that question. Okay, so with this circle, yeah.
Sir, in the origin there is 0, sir. How it is? In the
In
origin,
RHL there is 0.
How did you get, sir?
Where?
In the origin. Pole and 0 is there.
Origin. Oh, see, there is pole at 0. This is
Yes,
pole
sir.
at 0. Is it clear
Pole
now?
at 0. Yes, sir. But origin 0 also you have written now, sir.
No, it's 0. It's on. It's not. Oh, sorry. This is not. This is not 0. This is 0. Like, this is just that there is a pole at 0, which is origin.
Oh, okay.
Yeah. Okay. Thank you for this. So now with this circle, what I said, that if you have a transfer function of this type, and B is greater than A, then you obtain a circle, because you get break-in point and breakaway point both. And in that case, the center is given by minus b comma 0, and the radius is given by this, or other way around. You know the center is b, you know the breakaway point, break-in point, you can easily find the radius. So with this, can you solve this question? Quick question. Okay. The question is, root locus of s into s plus 2 plus k into s plus 4 equal to 0 is a circle. What are the coordinates? What are the coordinates of the center? Yeah, please solve it. We should be able to do it. Again, I'm writing it. Root locus of s into s plus 2 plus k into s plus 4 is equal to 0. So, circle, and what are the coordinates of the circle?
Minus 4 0.
Anybody else getting the same answer? Yeah, minus 4 comma 0 is the correct answer. Anybody wants me to solve this? Please try. If it is, if you're not able to solve it, then we can solve it maybe. Again, so for example, if you have a question like this, you're asked to find the root locus. If it is an like you are graphically you have been given the options. So can you guess like what will be the shape of this? Can you draw the root locus for this system? It will be a circle.
Circle.
Again, it's of the same form. But can you tell me the radius? Can you tell me the radius of the circle?
Minus
That's
2,
important.
comma 0.
Minus 2 comma 0 will be center, but
Yes.
I'm telling the radius of this circle. Yeah.
Okay, sir.
It should not take much time because you already know there are two ways. One way is the formula under root of b square minus ab,
Root 2.
and the second thing is root 2 is 1.414. No, again, but what should be okay? That should be radius. So with that, can you give me the break away point or break in point? Now it's conceptual. So if you have radius, the center is at -2. You know the breakaway point is on the real axis and the break-in point is also on the real axis, and that is on the boundary of the circle. So with that, can you tell me the break-in point and breakaway point? That is one way. That is one way of just looking at the diagram. But if you do not know the formula, what you do? If you do not know the formula, you'll find characteristic equation, and then you'll find the expression of k. And then after you find the expression of k, you find dk over ds, put that 0, you will get the values of s. And here you will get, in this case, you will get two values of s, and both will lie on the root locus. One will be break-in point, one will be breakaway point. But here, you know, there is no need of doing that. Why? Because it will be a huge calculation. You will have to apply the division rule, and there will be a lot of calculations. But you already know that root 2 is the center. Root 2 is the radius. So from that is 1.414. So -2 to 1.414 to the right of -2 and to the left of -2. So it will be -2 plus 1.414 and -2 minus 1.414. This will be minus 0.586. This will be 3.44. So this will be break-in point. This will be breakaway point. Anybody wants me to explain this more? Because -2 comma 0 is the center, and I know the radius, and I also know that break-in point and breakaway point lie on the boundary of that circle. So you just have to subtract that, and you'll get the answer. Just have to add that. Anyway, let's do one last question from today, and then you should be able to. There are many good questions, but time does not permit me to solve them because they will take longer. So let's see whether we can solve any good question or not, or whether there is any question from the assignment, practice assignment. That angle thing, did you understand that properly? Like, how do we find the angle? Because there are some questions in the assignment. Whether the angle is in first quadrant, second quadrant, third, you should be able to apply. There are other rules, but like angle of departure, angle of arrival, they're very important. You should be able to apply them. S into S plus 1. Okay, yeah, let's do one last question. That is given by, you are given, consider a feedback system with characteristic equation as 1 plus K 1 divided by S into S plus 1 into S plus 2. And draw the approximate shape of root locus. We need to draw the root locus. Let's go step by step. This is the last question, so I'll solve it fully. So first of all, we need to find the number of branches. Number of branches will be 3. And because number of poles are 3, so the number of branches will be 3. And all these branches will terminate at infinity. Correct? Because there is no 0, right? So because P minus Z is 3. Okay, so what are the poles? Poles are 0, 1, 0, -1, and -2. So let me draw an approximate shape. So I have a pole here at 0, then at -1, then at -2. I know this is a valid region, this is not a valid region, and this is also a valid region. Right? So this is very, very clear. Now, I know that all the branches will have to go to infinity, but through asymptotes. So I need to first of all find the angle of asymptotes as well as the centroid. So whenever you have 3 P minus Z equal to 3, then the theta will be, theta 1 will be 60. This is very easy. You just have to put the value 180 degree and 300. Right? And what is centroid here? Let's assume sigma A is the centroid. Centroid will be -1 -2 over 3. That will be -1. So again, you have a centroid as a pole, but not a breakaway point this time. It's a pole. So let's draw this asymptotes. One is at 60 degrees, so it will be something like this, or more clear. Wait. Let's assume I have a -1 here. This is 60. Then I have 180 will be like this, 180. Then I have 300, it will be like this. Right? So I drew 3 asymptotes. Then my centroid is at -1. Now I know my valid root locus is this. It will go like this. I will come like this. There will be a breakaway point in between. This is 1. And this will not be a valid root locus area. So skipping it, and this will be my valid root locus area, and it will go to infinity along this asymptote as well. Right? So this is minus infinity. Correct? Now I have 2 poles, 2 branches left. One is this, and other is this. Right? So now we need to first find the breakaway point. Right? How I told you to find the breakaway point, we'll find characteristic equation, and we will find that in terms of, K, right? So I'll directly write that. So characteristic equation in terms of K will be minus S square plus 3S square plus 2S. So if you write dk over ds equal to 0, it implies you will get S as minus 0.423 and minus 1.57. But if you see, minus 1.57 is not the part of root locus, therefore the valid breakaway point is minus 0.423. So it's here, minus 0.423. So how I will draw this root locus, my branches will come like this. And here they will go to origin like this, because they have to go to infinity and they will go across asymptotes. Right? So this is the complete root locus of this question. But now there is one more thing. If you can see, this root locus is touching imaginary axis. This root locus is touching imaginary axis. So at what point this root locus will touch imaginary axis? That means at that point, my system will be marginally stable. And how we find that? That is given from Routh's criteria. For example, the characteristic equation, if you write, it will be s cube plus 2s square plus s square, sorry, it will be 3s square plus 2s plus k equal to 0. And then if you draw Routh's array S3, S2, S1, and S0, will be 1, 2, 3, k, 6 minus k over 3, 0, and it's k. So now, in order for this system to touch the imaginary axis, this has to be 0. It means k has to be 6. When k is 6, so this becomes 0. So when this becomes 0, we need to find the auxiliary equation. That will be 3s square plus k equal to 0. And it will be 3s square plus k is 6 equal to 0. It will be s square minus 6 over 3. S square is equal to minus 2, or s is equal to plus minus root 2j. Right? So plus minus root 2j. So it means my root locus, it intersects the real axis. This is root 2. This is also minus root 2j. And this is root 2j. So sometimes you are being asked to give the point where the root locus intersects the imaginary axis. What you have to do, you just have to apply Routh's criteria, find where the system is marginally stable, get the row of zeros, get the auxiliary equation, solve auxiliary equation, and find the roots. Those roots will be the intersection with the imaginary axis. So with this, I think you should be able to solve most of the problems. But yeah, again, for that question where a circle is given and you have to find the maximum overshoot, I think that is the correct approach to handle that, where theta is cos of gamma, gamma you'll get, then you'll find the overshoot by that formula. I think that is the correct way to approach that. But in any case, if you're not convinced, we can solve that maybe in the next week. So any question, if you do not have any questions, we can maybe stop. And thank you very much for attending.
Sir, I have a
Thank
question.
you. Thank you very much.
Yeah. Yes,
Sir, I have
please.
one question.
Yeah.
Sir, in week 3, we see one problem.